Welcome to the IUPI Well Completions Overview module of the production operation phase in the E&P lifecycle. Before beginning this module, you should already be aware that the completion or inflow system is a critical component of the well design. Understand that specific considerations must be acknowledged to design the optimal completion. Have basic knowledge of casing designs, as well as drilling, cementing, and perforating operations. And realize that specific information can be obtained from various sources to help design an effective completion. This training module will introduce you to various well completion considerations. After finishing this module, you should be able to identify the sources of pertinent well data related to completion design. Identify the two most important functions and the primary objective of a completion fluid. Associate various formation damage mechanisms with their causes. Define the intervals needing adequate cement bond integrity when designing a completion. Recognize when remedial measures are necessary to rectify an inadequate cement bond. List the basic ways to prepare a liner for inflow. When preparing a well for completion, specific operations must be successfully accomplished. To accomplish the necessary operations, the following are required: a properly designed completion fluid, an understanding of fluid properties and formation damage mechanisms, comprehensive consideration of changeover procedures, adequate cement bond integrity. The completion choices may determine the success or failure of a well. To optimize the completion, it must be consistent with the produced fluids and rates expected, the anticipated use of the well over the field life cycle, bottom hole orientation, completion fluids, and logging and testing requirements. The well completion has an impact on, or is impacted by, borehole stability or consolidation, characteristics of fluids exposed to the reservoir, depth of filtrate invasion, and hardware such as casings, cementing, and completion equipment. The production engineer is responsible for coordinating the completion design, typically with cooperation from the geologist, the reservoir engineer, the well engineer, and the well site supervisor. Additional specialists may be required for the completion design of a particular well. It is important for all personnel involved to understand the input from the various experts involved with the completion design. This will result in an effective and feasible bottom hole design and producing configuration. The topics in this module will introduce you to the approach to well completion design. To properly prepare a well for completion, specific information about the well must be acquired. By combining the information with the well objectives, you can properly prepare the well for completion with the inflow system. The sources for this information include hole profile and casing design, offset wells, drilling report, mud logs, drill stem testing, also called DST, and formation testing, electric logs, core analysis, and completion design. Completion fluid is a special fluid placed in the wellbore after the well is drilled. Completion fluid remains there for the entire completion phase of the well. Changing over from the drilling fluid to the completion fluid is typically the first step after completing drilling operations. Changing over marks the beginning of the completion operations. In this phase of the operation, you need to consider both the function and objectives of the completion fluid. The two most important functions of a completion fluid are maintaining well control and effective solids removal. The primary objective of a completion fluid is minimizing formation damage. while keeping an eye on costs. The two most important functions of a completion fluid are to maintain well control and remove solids effectively. Due to safety and environmental considerations, well control is the foremost function of the completion fluid. The hydrostatic head of the fluid column must be greater than the static reservoir pressure to maintain well control. The differential pressure between the wellbore and formation should be minimized to prevent excessive completion fluid loss to the formation. A differential pressure safety margin of 100 to 200 psi is a general rule of thumb. However, experience with local conditions should override any generalization. The completion fluid must remove solids from the wellbore following drilling operations. Solids removal is accomplished by pumping the completion fluid down the well and back to the surface. This pumping operation is commonly referred to in the field as circulating. Changeover is the specific circulation procedure where completion fluid displaces drilling mud in the wellbore. Changeover operations begin after the wellbore is drilled to the target depth and the casing is run, if not an open hole completion, and before perforating occurs. During changeover, the completion fluid not only flushes the drilling mud out, but also any drilled cement, scale, or other residue in the well. The solids are carried out of the well and then separated from the circulated completion fluid at surface. It is important to remove undesirable particles from the completion fluid before it is circulated back down the hole. Ideally, a completion fluid system should be free of solids when contacting the formation to minimize solids-associated formation damage. To achieve the highest well productivity possible, formation damage should be minimized during well engineering operations. Completion fluids, like drilling fluids, can be a major source of formation damage. The primary objective of a completion fluid is to minimize formation damage. All wells are susceptible to formation damage. Most types of formation damage are due to physical and chemical interactions of the completion fluid with the reservoir rock and formation fluids. Completion fluid and its filtrate can react with the formation fluids to create an emulsion or swell certain types of clay. Solids in the completion fluid can cause considerable damage by entering pore throats to impede fluid flow. Formation damage can have a profound impact on production rates and overall reservoir recovery. Costly remedies may be attempted to remove formation damage without guaranteed success. Therefore, it is important to take extra care in designing and maintaining completion fluids. For example, any additives used must be carefully selected for specific purpose and compatibility. This is particularly important for open hole completions. The potentially high cost of completion fluids can tempt the well engineer to cut corners. However, cutting corners may compromise the ability of the fluids to achieve its objective in minimizing damage. Fluid design criteria are determined after extensive analysis, discussion, and optimization. If cost savings are made by ignoring design criteria for minimizing formation damage, money may be lost due to more rig time, expensive remedial operations, and reduced productivity index. In the previous section, we learned that the most important objective of completion fluid is to minimize formation damage. Here are some important damage mechanisms and their causes that can influence the design of the completion fluid. Emulsions occur when two immiscible fluids come into contact with one another. Emulsions are highly viscous and act to clog pore space. This reduces the effective flow of reservoir fluids to the wellbore and is therefore a form of damage. Predicting emulsion formation can be accomplished by studying produced reservoir fluids in the laboratory. These studies will indicate the need for emulsion-breaking chemicals in the completion fluid. The removal of emulsion damage is difficult to manage. Cleanup may occur naturally or not at all. A very common emulsion is formed when you mix oil and vinegar as a salad dressing. Small oil droplets are dispersed throughout the vinegar. Clay swelling occurs when fresh water comes into contact with formations that contain clays, such as smectite. Smectite, also known as montmorillonite, is one of several clay types that cause swelling. Another clay type, kaolinite, is shown here. Swelling causes the pore space of the formation to decrease, reducing permeability. Laboratory analysis of formation cuttings can indicate the presence of these clays. This information will be found in the mud logs. To minimize potential damage when swelling clays are present, use completion fluid with potassium chloride, or KCl. The typical concentration is in the range of 2%. Mobile particles are formation material that can be dispersed by fluid movement. Formations that may be affected by this damage mechanism are those which contain clays like kaolinite and illite, and minerals such as feldspar. Mobile particles are often referred to in the oil field as formation fines. You may hear the term fines migration to describe this damage mechanism. The movement of these mobile particles can lead to plugging of pore throats, which therefore reduces permeability. Gradually increasing the production rate can help clean up these particles or fines and thus minimize formation damage related to mobile particles. Precipitates are solids which form in solution when incompatible fluids come into contact with one another. For example, when calcium chloride is added to seawater, calcium sulfate precipitates from solution. Precipitates like calcium sulfate can invade and damage the formation. Fluid compatibility studies are necessary to determine if precipitation is going to be a concern. Design a completion fluid with the proper chemical additives that will prevent precipitate formation. Scale, related to hydrocarbon production, is a depositional accumulation due to interactions of incompatible fluid components and changes in conditions. Scale typically occurs in completion equipment, tubing, pipelines, and surface equipment, or at the formation phase. Scales form due to the incompatibility between completion or injection fluids and formation fluids during changes in system equilibrium, pressure, temperature, gas liberation, etc. Scale damages the formation by entering and clogging the pore space, reducing the well's production. Scale inhibitors, or sequestering agents, can significantly reduce scale levels. Acid treatments can be highly effective in removing formation damage caused by scale. Bottom hole orientation refers to the particular trajectory of the borehole through the formation. There are three basic types of trajectories that are used: vertical, deviated, and horizontal. The borehole trajectory through the reservoir depends on several factors. The path selected must take into account permeabilities, reservoir boundaries, and fluid contacts. The ideal path desired by the reservoir engineer or geologist may not be economically feasible due to a number of other factors, such as surface location constraints, geology along the path, rig equipment limitations, and intermediate constraints such as faults and other wells. The actual bottom hole orientation is therefore one which will produce the reservoir most efficiently after accounting for economic considerations. A vertical well is generally the least expensive option for drilling to a single target. A vertical well will be drilled in any appropriate situation when the drilling rig can be placed directly above the intended target. The majority of exploration wells are vertical wells. A deviated well may be drilled when the surface location cannot be located directly above the intended target. A normal deviated well is the most common type of well currently drilled. Normal deviation is a generally accepted term to describe a single borehole with less than a 60-degree inclination. There are many development situations where wells need to be drilled from the same proximate surface location. Offshore platforms can have as many as 50 or more wells drilled from the same facility. Arctic installations demand a similar approach in the way that the boreholes are oriented. Densely populated areas may also require that wells be deviated due to high land prices and local government restrictions and policies. In addition to surface considerations, orienting a well to reach a trap under a salt dome may also require a deviated well. Horizontal wells increase wellbore exposure to give increased productivity. Since the early 1990s, improved technology in downhole directional and surveying tools, rig equipment, and completion techniques have allowed efficient production from fields that would be uneconomic using conventional directional wells. After a well is drilled to TD, or total depth, it must be completed. There are 3 basic ways to complete a well: open hole completions, liner completions, and cemented casing completions. In this section, we present each completion option, along with the advantages and disadvantages of each. Because the cased and cemented completion relies on the quality of the cement job, methods used to evaluate cement integrity are introduced. An open hole, or barefoot completion, is one with the casing set above or just in the top of the producing formation. The reservoir is drilled, but no pipe is placed or cemented across the formation. An uncemented liner completion is one in which a smaller diameter casing is set above the producing zone and extended through the producing interval. The top of the liner generally overlaps the bottom of the casing 50 to 100 feet. The liner is typically anchored in the casing using a liner hanger. A cemented liner completion is one in which casing is set above the producing zone, and the liner, which extends through the producing interval, is cemented into place. The liner is then selectively perforated for production. A cemented casing completion is one in which production casing is run and cemented across the production zone. The casing is then selectively perforated in order to produce the well. This completion is by far the most common type of completion. An important aspect of a cemented completion is the quality of the cement that fills the void between the casing and the side of the drilled well bore. This space is more commonly known as the annulus. If cement was not placed in the annulus through fluid-bearing zones, any fluids would be free to move about, uncontrolled, from one part of the well to another. Certain intervals may need adequate cement bonding above, within, or below, for reasons such as safety considerations. Uncontrolled flow outside the casing could lead to dangerous annular pressure buildup. Environmental concerns. Fluids from the production zone must be prevented from traveling up to and contaminating any freshwater zones, which could prove environmentally disastrous. Economic reasons. Zone segregation isolates undesired intervals in the formation itself, ensuring that no water or gas is produced with the oil. Not keeping water or gas out can easily make the well uneconomical. A cement bond log, also known as a CBL, is therefore run before perforating to determine the quality of the cement job. The cement bond log can detect varying degrees of cement bonding. These sections from actual CBLs display both good and bad cement bonding. Cement bond evaluation is beyond the scope of this module. However, the importance of determining adequate cement bonding needs to be recognized. We have just learned that there are several different completion types. With the exception of the cased and cemented, or cemented liner completion types, the borehole is in communication with the formation. Cemented casings and cemented liner completions, however, require a procedure to establish communication between the formation and the wellbore. This procedure is called perforating. In this view, we see a typical well completion prior to perforating. To allow formation fluids to enter the wellbore, the casing is perforated using a perforating gun. A perforating gun contains specially designed explosive charges. The gun is positioned across the target formation and then fired. Fluids from the formation can now enter the wellbore. Engineers rely on open-hole logs to decide where to perforate. Well logs, such as resistivity logs, are used by the engineer to determine perforating intervals. Analysis of open-hole logs provides an accurate profile of oil and gas accumulations present in the well. In this reservoir, we see the gas zone in red and the water zone in blue. The target oil zone lies between the gas and water. The general strategy is to maximize the length of the oil zone perforated, while at the same time limiting the potential for water and gas production. This is accomplished by not perforating too close to these two zones when perforating the oil zone. In the absence of local experience, not perforating within 15 feet of a water zone or within 20 feet of the gas zone should be adequate. Now that you have completed the well completion overview module, you should be able to meet the following objectives. Identify the sources of pertinent well data related to completion design. Identify the two most important functions and the primary objective of a completion fluid. Associate various formation damage mechanisms with their causes. Define the intervals needing adequate cement bond integrity when designing a completion. Recognize when remedial measures are necessary to rectify an inadequate cement bond. List the basic ways to prepare a liner for inflow. Let's review some of the major topics covered in this module. The Well Information section noted several sources of well information, as well as their possible applications. In the next section, we discuss the need for completion fluids to maintain well control and remove solids. Formation damage mechanisms were introduced, along with some basic cost-benefit arguments to using premium fluids. In the section on formation damage, we define the various mechanisms whereby a formation can become damaged. The next few topics dealt with the physical configuration of the well. These sections on bottom hole orientation and completion configurations touched on the strategies used to assign well architectures. The importance of cement bond integrity and its analysis was stressed during our discussion of cemented casing wells, the most common completion configuration. And in the final section, we examine the basic procedure whereby mechanical communication between the casing and the reservoir is established: perforating. Some general guidelines and rules of thumb were used to suggest perforating strategies for a well in which oil and gas are present in the pay zone. Much of the knowledge that you gained in this section will be applied in the Completion Challenge module.